Hello everyone, this is Homer White, one of the instructors of Math 111 at Georgetown College. We're now in Chapter 2 of our course, Describing Patterns in Data. This is Part 1 of the video lectures. So in this section, we will be looking at some basics of data and how it comes to us in the form of data frames. And we'll also be looking at the types of variables that we see in data frames. Then we'll talk about how to describe the distribution of a variable. We'll also look at how you can use the idea of distributions to explore relationships between variables. Along the way, we'll see that there are two basic ways to describe distributions. One is through numerical measures, and another is through graphical tools. So in Part 1, we're going to be looking first at the types of variables that you might find in a data frame. We'll look at research questions that you might ask about data that you have on hand or that might have motivated your collection of that data in the first place. Then we'll talk about how to describe the distribution of one-factor variable. Then we'll look at the relationship between two-factor variables and how to discuss those. And then we'll get into the first part of describing the distribution of one numerical variable. Always remember to make sure that you have loaded the necessary packages. This can be done by typing in the following code that you see, but it can also be done by making sure that the little box next to the package name is clicked when you look in the Packages tab in the lower right-hand corner pane. So, types of variables. We'll need an example data frame. So let's look at M111 survey. This was a survey given to 71 students who were enrolled in Math 111, all of the sections of that course, at Georgetown College back in the fall of 2012. Now, by virtue of the fact that the TigerStats package is already loaded into your session, this data is accessible to you. But if you want to get an explicit and close look at the data, you actually need to put it into your global environment, and this is done with the data function. And for the moment, I'll just take you back to the server. In fact, I assume you might be following along looking at this presentation document in the RStudio server itself. So let's say you're there and looking at the presentation document up here in the upper right-hand pane, and say you'd like to get this particular item into your workspace, so you might copy and then go down to the console and paste in this function and then run the code. And if you just take a quick look at your environment, you'll see that Math 111 survey has come in as a promise, so it's sort of halfway there. To actually get a look at it, you need to view Math 111 survey. Let's copy and paste that. Of course, you could type this for extra practice, type it directly. And when I run view Math 111 survey, then I actually get a look at the data in the form of an Excel-like spreadsheet where the rows stand for individuals, students who were in the survey, and the columns stand for variables that were measured on these students. You always want to read your data in context, learn as much about it and how it was collected, who collected it, and why as you possibly can. So for that, you might want to ask for help. So if we do so, then in the lower right-hand tab under Help, we get a look at the documentation for this data set in the TigerStats package. And scrolling through the documentation, we can see what exactly all the variables mean. So for example, height is how tall are you in inches. And we also find out the source of the data set In other documentation, you'll often learn quite a bit more about the data frame at hand, so it's always good to look at help. Okay, let's go back to the main PowerPoint. I'd like to point out that a shortcut for help is simply question mark followed by the object that you would like to get help about. So here's part of the view of Math 111 survey that you saw in the upper left-hand pane. So we have the rows, which are observations or individuals, subjects in your study, and the columns, which correspond to variables that were measured on these objects. You should know that there are two major types of variables. There are factors and there are numerical variables. Factors are also called categorical variables because their values are categories and not numbers. Their values are also called levels. So for example, if you had the variable sex, that would be a factor variable. Its possible values are male and female. Those aren't numbers. There's some types of factors that are called ordinal in the sense that their possible values, their levels, come in some natural order. So for example, in the Math 111 survey, you'll find the variable seat. Where do you prefer to sit when you have a choice in a classroom? Do you prefer the front, the middle, or the back? Those come in a natural order. And if R is ever made explicitly aware of that order, it will actually call the factor an ordinal factor, though that won't have much of an impact on how you do your analysis. The other major type of variables are numerical variables, also called quantitative variables. These come in two subtypes called by R double and integer. Now doubles, which are also just continuous numerical variables, those are variables whose values can come in some range of real numbers. So in a data frame, they'll also often be recorded to some decimal approximation, maybe 2 decimal places, and you might see some possible values, 4.37, 2.58, and so on. But know that these are only a few amongst many, many possible values. There's also integer numerical variables, often called discrete variables. And those have more restricted values. The values have to be whole numbers, 1, 2, 3, 4, 5, and so on. One of the most important functions that you can use to learn about an object in R is the structure function, or the stir function. If you were to apply the stir function to Math 111 survey, this is the kind of output that you would get. Now, I should back up a moment and tell you that when you think about the structure of an object, there's really two major components to the structure. First of all is the kind of object that it is. So for Math 111 survey, the kind of object that it is data frame, and you see that written at the beginning. The second major component of the structure of anything at all, really, is some account of the parts of the object and how those parts relate to each other. So for a data frame, the parts of the object can be thought of as the variables. And Math 111 survey has 12 variables. They're related to each other in that they are all variables that are measured on the same set of observations, the 71 people in the survey. That's the relationship between the parts of this data frame. But R goes a little further. The variables themselves have a structure. They are of a certain kind, and then they have parts. So for example, the variable height is a numerical variable, and that's indicated to you right here. And then some nod is made towards the fact that this variable has parts. Those are the heights of the individuals in the study, and the first few of them are given next. Now, as a quick tip, if we could dip back once more into the RStudio session, if you wanted to look at the structure of a variable and you didn't want to use this space here to look at the whole view, maybe you had something else there you were working with, you could simply go to the object in the workspace and click on the little button next to it, and the structure comes out. That's a very handy thing to have available. Okay, back to the data, back to the presentation. So the next section is research questions. Right now we're in the part of statistics that's called descriptive statistics. This is the art of summarizing data and describing patterns in the data. The tools you'll have at hand for descriptive statistics are of two types. There are graphical tools and numerical tools. The graphical tools include bar charts, histograms, density plots, and box plots, and many, many more besides the ones that you're going to learn about in this chapter. And they're often very exciting and very informative and a lot of fun to produce. There are also numerical measurements that you can make on your variables. So in this chapter we'll learn about the mean and the standard deviation, the median and the interquartile range. We'll learn about quantiles, and there are many more numerical measurements that we'll come upon as the course goes along. A really important guiding principle is that the choice of the tools that you will use really depend on the type of variables that are involved in your research question. So we should get to research questions. What are they? Here's some examples of research questions that you might ask once you're confronted with the Math 111 survey data, or they're questions that the students themselves might have been asking when they collected the data in the first place. So for example, research question: are a majority of students female? This turns out to be a question about one of the variables in the data frame, namely the variable sex, which is a factor variable. I've just done a very important thing. I call it variable analysis. I find the variable of interest in the research question, and I decide what kind of variable it is. Another example of a research question: who's more likely to prefer to sit in the front, a guy or a gal? Now here, we're asking a much more interesting research question, I think, one about the relationship between two variables. The variables at hand are sex, which is a factor variable, and seat, where do you prefer to sit in class, front, middle, or back? That again is a factor variable. Another research question: who drives faster, students who prefer the front, the middle, or the back? Again, this is about the relationship between two variables: seat, a factor variable, and fastest, a numerical variable. In each of the cases where we have been confronted with the research question, we've been very careful to pick out the variables involved in the question and to classify those variables. That's variable analysis, and the importance of this analysis will come more and more clear the more we do our work. So let's first start with research questions that involve the distribution of one factor variable. So from our examples, I might pick out: what percentage of students in the survey are female? This was the one that involved a single factor variable, sex. There are numerical and there are graphical tools for engaging in this research question. The numerical tool would be tables. Now, in its base form, a table is just a tally of the counts of the different possible values of the variable that were found in the data. And it's done by the xtabs function. If you apply xtabs to the argument twiddles and sex, we'll talk about twiddles later, but sex is the variable of interest, and then the argument data equals Math 111 survey, and notice how both of these arguments are separated by a comma and they're enclosed in parentheses. This is the case for all our functions. Then you get a simple count of the males and the females in the class. That's not quite an answer to our original question, which asked about percents. So if we go to the row percent function, which is in the TigerStats package, and apply that to the table, so we simply have a repeat here of the command for the table, and that itself is inside parentheses, and the row percent function is applied to it. Then we get the percentage of females and males who are in the study. So apparently 40 divided by the 71 total number of students was 56.34%. That's the percentage of females. And the 31 males divided by the 71 was 43.66%. Those two percentages constitute what we call the distribution of sex in the sample survey. The total here at 100% is just a polite add-on to indicate that percentages are being used. The graphical tool that goes along with either tally tables or percent tables is bar charts. So we have from the TigerStats package bar chart GC, and what you do is apply it again to this formula, twiddles sex. Again, you need this argument that tells you what data frame is at issue, but another couple of arguments condition the look of the box plot. There's the type, and we're going to look at percentages because we're interested in the distribution. And it's always a very good idea to include a title for your graphic, and titles are fixed by the argument main. And so this is the result of applying that function. And you can see that more than 50% of the people in the class are female. The percent rectangle for the females is higher than the percent rectangle for the males. Next up is the relationship between two factor variables. So how do you address research questions where two factor variables turn out to be of interest? As an example, let's take the research question, who's more likely to sit in the front, a guy or a gal? Now this question is about the relationship between two variables. The variables involved are sex, which is a factor, and seat, which is a factor. But the variables have a somewhat different feel about them. There's a sense going around, and it's not confirmed in any data yet, but there's a sense going around that your sex causes other types of behaviors about you, maybe through cultural conditioning or something like that. And maybe your sex, plus the cultural conditioning that people subject you to once they discover what sex you are, might explain something about where you choose to sit in a classroom once you get to be older. So we think of sex as the explanatory variable in this research question, and we think of seat as the response variable. Generally, the explanatory variable is the variable that we are under the impression might help cause the response, or that we simply might intend to use to predict the response, whether it causes the response or not. I stress that we don't always use an explanatory response distinction. This is just something in our minds that helps us organize our thinking sometimes. R itself knows nothing and cares nothing about a distinction between explanatory and response variables. So, the numerical tool for examining relationships between two factor variables is two-way tables. These are also called cross tables or contingency tables. The code again involves the function xtabs, and I think now you might recognize the x as short for cross and tabs table, cross table. This time in your formula, you have to include both sex and seat. And as a general rule, it's probably going to be easiest for you to read and interpret and describe the results if you put what you think of as the explanatory variable first. The plus in the middle simply separates the two variables for R's convenience, but it's chosen by the programmers because it looks like a cross, so it reminds us of cross tables. And again, there's an argument, data equals Math 111 survey, that tells R where to look for those variables sex and seed. So the output of the function is here. However, I don't think that this two-way table answers the research question very well. We could tell that there are more people in the study who are both females and who sit in front. There are 19 such people. Then there are people in the study who are males and who sit in front. There are 8 such people. But comparing the 19 and the 8 doesn't really answer any questions. The reason is that there are more females in the study in the first place. There are 40 females in the study. There are only 31 males. So we would expect more females in the cells that are in the top row than we would expect for there to be males in the cells in any of these second rows, just because there's more females in the study. What we really need here are percentages. So what we're going for is something that's called conditional distributions. There are 2 conditional distributions in this study. There's the distribution of seat given that sex is female, and there is the distribution of seat given that sex is male. The way that we get these conditional distributions is we produce the cross table, the original cross table, but for convenience, let's go ahead and just store it in an object. And you can name the object anything you like, but I strongly suggest that you name it something that you've not seen named before with the same name, and that you don't expect to ever have to use for something else again. But it should also be a descriptive name that reminds you of what's in that object. So I thought sex seat was pretty descriptive, and it's going to contain that cross table. And then, if I apply row percents to the cross table that's in sex seat, then I get the same cross table but with row percentages instead of counts. And what I've got going across this first row here is a set of row percentages that constitutes the conditional distribution of seat given that sex is female. And in the second row, I've got the conditional distribution of seat given that sex is male. Now with these row percentages, we can really begin to make some meaningful comparisons. For example, we see that nearly half of the women in the study preferred to sit in the front, whereas only about 1/4 of the men in the study preferred to sit in the front. That looks like a big difference, and that indicates to us that there's some relationship between sex and seat, that guys and gals do differ in their seating preferences. Gals tend to prefer the front at a greater rate than guys do. You can also make a bar chart of the same thing. But before we show the bar chart, let me back up and talk about some of the input you've been seeing in some of these functions. It's called formula data input. The formula is the argument that has a twiddles in it somewhere. This signals to R that the argument is a formula. What else is in the formula depends on the type of analysis you're trying to do. But at a minimum, it's going to have the names of the variables that you are interested in, and it's going to have some other symbol called an operator that helps to specify the type of analysis that is of interest. In this case, we're in a two-way table, a cross-table situation, and that plus was probably selected by the programmers to remind you of cross tables. The second part of formula data input is the data, and this is an argument that simply says, where is R to look for the variables that appear in the formula? What data frame should it consult? And it should consult M111 survey. The other arguments condition the specific look of the graphical object, but they are not part of the formula data input itself. But you'll see formula data input the rest of the year. Here's the output of that bar chart command. And you can see right away that there is a difference in the conditional distributions. You can see that the light-colored rectangle that stands for preferring the front for females is the tallest rectangle there is. Nearly half, nearly 50% of the females prefer the front. Relatively few of the females prefer the back. Whereas look at the guys. Only about a quarter prefer the front. Over half of them prefer the middle. So quite a few differences there to see and to talk about. Now let's consider the distribution of one numerical variable. How might we attack research questions where a single numerical variable is the focus of interest? So let's take that research question. How fast do Georgetown College students drive when they drive their fastest? This involved one variable from the M111 survey data frame. This is the variable fastest, which is numerical. When you're describing a numerical variable, you want to describe its distribution. But the distribution of a numerical variable is a richer and more complex thing than that small set of percentages that give you the distribution for a factor variable. It's so rich that we really can't just lay it all out for you all at once. So we're going to give you just a few summaries of the distribution, and then gradually over the course of weeks come to a clearer and clearer idea of what a distribution is for a numerical variable. The summaries we have in mind are measures of the center and the spread of a distribution, and these will be numerical measurements. But we also want to summarize and describe the shape of the distribution, and we'll do this with a variety of graphical tools. So heading for the numerical measures. A convenient way to get a lot of numerical measurements for a numerical variable is the function favstats from the Mosaic package. Favstats works with the familiar formula data input, so you have a formula consisting of just the variable fastest with the twiddles in front to alert R to the fact that a formula is there, and then again the data argument. So you get a number of different statistics, most of which are mysterious at this point, and we'll learn about them one by one. So you get the min, that's the smallest data value, so the slowest anyone ever drove when they were driving their fastest was 60 miles an hour. You get the first quartile, the median, the third quartile, the max, so apparently someone claims to have driven 190 miles per hour. You get the mean of the data and the standard deviation of the data, and you also get the sample size, the number of people who actually answered the question, what's the fastest you ever drove? So let's focus in on the mean out of that list of numbers. Now, the mean of sampled data is symbolically denoted by an X with a little bar on top. And here's how you find the mean. First of all, you look at the individual data values themselves, which are symbolized X sub I, and you add them together. That's the sum sign. After you've gotten the sum of all the values, you divide by n, the number of values in the list in the first place, the sample size. So although favstats will compute this for us automatically, it's good to try it out ourselves for just a small bit of data. So here's a fake data set, and you can construct any list of numbers you like using the C function. So let's put the numbers 2, 4, 7, 9, and 10 together into a little list using that function. And let's store it in an object. How about the name fake data? And then if you ask for the mean of fake data, you get 6.4. Now, this is a very small data set, so you could have just tried it by yourself using R as a calculator. Just add the 5 numbers together and divide by 5, the number of numbers that there are, and yes, you really do get 6.4. Now, the mean describes the center of the data. It describes a typical value. It tries to describe a value that hopefully a bunch of other values are near. But you also want to describe the spread of the data, and the standard deviation is a measure of spread. The idea of the standard deviation is to measure how far the typical data value is from the mean of all the data. The formula for it is fairly complicated looking, but here's the basic idea of how it comes together. First of all, you find the mean of all the numbers. That's this x bar that you see. And then you're going to subtract the x bar from each of the data values, and you get what are called deviations. And then you're going to square these deviations. And then after you've squared them, you're going to add up those squared deviations. And then notice the divide sign here. You're going to be taking an average. Well, it's sort of an almost average, because instead of dividing by n, you're dividing by n minus 1, the number of values minus 1. After you've done all that, you're going to take the square root of this almost average, and the result is the standard deviation, which we denote by a lowercase s. Whew! We'll think a little bit more about computing that, but what I really want you to know is how to use these two numbers, the mean and the standard deviation, together to give people an idea of what those fastest speeds are like. So once you know the mean and the standard deviation of a numerical variable like fastest, interpret it in a little sentence like this. So for fastest, you might say, the typical Georgetown College student drives about 105.9 miles per hour, give or take 20.8 miles per hour or so. So the standard deviation is sort of a give or take figure. And it does a great job, along with the mean, of describing where most of the data values are. In most data sets, a majority of the data values will lie within one standard deviation of the mean. So if you think of 20 as the standard deviation and the mean is, say, 106, then you know that most of the speeds are probably between 86 and 126 miles per hour. That's something you can very quickly think if you know the mean and the standard deviation. Back to computing the standard deviation, it's good just once to run over a small example. So let's take fake data again. And let's take the mean of it, and yes, it was 6.4. And then let's subtract that 6.4 from each of the xi's, from each of the data values x. And you get some numbers that were below the mean, and so the deviations are negative. Sorry, here. These two are negative. And you get some numbers that were above the mean, and so they have positive deviations. Now the fact is, we care about how far a value typically is from the mean, and we don't care whether it was above or below. So what we do to get rid of the negatives is we square all of these deviations, at the cost, of course, of making some of those numbers rather larger than we would like. Once we have taken the squared deviations, then you do your almost averaging. You add them together, divide by one less than the number of numbers that there are, and the result at this stage is called the sample variance. But it's much too big a number to say how far the typical data value is away from the mean. And that's because of all that squaring. So to sort of make up for the squaring, we take the square root and we arrive at the standard deviation, 3.3 roughly. Now if you think of your original list of numbers, and the mean was 6.4, and you go 3 units, the standard deviation, back and forth, so that's from about a 3 to about a 9, you realize that actually covered almost all the numbers in the list. So sure enough, most of the numbers are within one standard deviation of the mean. Now there's another measure of center that's also popular. It's called the median. So once again, looking at our fake data, the median of the fake data is 7. Now how does it work to find the median? What is it? It's an attempt to find the middle value of the data. So if there's an odd number of numbers, and you sort those numbers, say from smallest to largest, as fake data is sorted, then there will be a unique number in the middle. So with 5 numbers, the third number is the one exactly in the middle, and that's the median. Now, if there had been an even number of numbers, then there would have been 2 numbers that were equally close to being the middle, and you would just average those 2, and that would be reported as the median. That's how R finds a median. Now, we'd like to talk about a measure of spread that maybe is a competitor for the standard deviation. But to get up to that idea, we're going to have to introduce the notion of quantiles or percentiles. And these are important in their own right. So let's pause and talk about them. So for every percentage, from 0% to 100%, there is a percentile or a quantile associated with that percentage. And we'll talk first about what they are and how to interpret them, and then we'll talk about the code here that produces them. So what are they? Well, there are many percentiles, but the 20th percentile of the fastest speeds is 90 miles per hour. What does that mean? It means that about 20% of the students drove slower than that speed. The 50th percentile of the fastest speeds is 102 miles per hour, and that means that about 50% of the students drove slower than 102 miles per hour. Now that sounds like the middle, and in fact, the 50th percentile is the same thing as the median. We also see that about 80% of the students drove slower than 120 miles per hour, and we would say that the 80th percentile of the fastest speeds is 120. And we would say that the 90th percentile of fastest is 130, meaning that about 90% drove slower than 130 miles per hour. Of course, you can think of things a little bit reversed. You could say such things as about 10% drove faster than 130 miles per hour. Or you could say about 80% drove faster than 90 miles per hour. But that's how percentiles and quantiles work. Here's how you get them. So the basic function is quantile, and you ask for quantiles of your variable, in this case fastest, and there's an extra argument you need to provide that says what particular quantiles you want. And so if you want the 20th, 50th, 80th, and 90th, then you simply enter them as a list here with the C function, enter them as decimals rather than percents, and feed that to the probs argument of the quantile function. Now, you're going to have to tell R where to look for the variable fastest, and unfortunately quantile does not recognize formula data input. So what you do is you say with the data frame Math 111 survey, do the following. Take the quantile of fastest with those probs. So that's one of the very few times in this course when formula data input won't be available for you, possibly the only time. Now amongst the quantiles, 3 are particularly important. The 25th, 50th, and 75th percentiles are most important. The 25th percentile is called the first quartile of the data because 1/4 of the data lies below it. We've already met the 50th percentile as the median, and the 75th percentile is the third quartile of the data because 3/4 of the data lies below it. Or, thinking of it another way, 1/4 of the data lies above it. Now we can finally talk about describing the spread in a way alternative to the approach of the standard deviation. Our notion is that of an interquartile range. And the interquartile range, or IQR, is simply the third quartile of the data minus the first quartile. Now, thinking about how 1/4 of the data lie below the Q1, and 3/4 lie below Q3, therefore 1/4 lie above Q3, then we see there's 50% left over in between the Q1 and the Q3, and it's the middle 50% of the data. So the interquartile range is telling us how spread out the middle 50% of the data are. Just as you combine the mean and the standard deviation to describe center and spread, you can combine the median and the interquartile range. And so you might give a report something like this. For the fastest speeds, the median fastest speed driven was 102 miles per hour. There's your description of the center. And you can say the interquartile range was, and then you subtract third quartile minus the first, 29 miles per hour. Probably the most instructive way to put it, though, is in this final sentence. The middle half of the students drove between 90.5 and 119.5 miles per hour. That's a good way to talk about the spread. So in the next part, we will begin with some tools that address this question: how do you describe the shape of the distribution of a numerical variable? Thank you for listening.